Right, good morning everyone. Welcome to the biggest section of the chapter. It's the one that you ask most questions about, and it is one of the profound changes of ideas in physics. Kinetic theory and this diagram actually comes from the video that you need to watch first. So do watch the PowerPoint, click on the photo and you'll get the video comes up. So you can see Brownian motion. We can see the effect of these tiny particles that Einstein was the first person to actually show that they existed. His first paper in 1905, the second one same year was the photoelectric effect, and so on. So ground changing stuff, okay? But it was Boltzmann that introduced this idea of statistics into physics. Until then, everything had to be measured. So this is his work and this is his proof that brings it together. So, when you've seen the video, you'll have seen about Brownian motion. You'll have seen the tiny white dots, which are big enough for you to see, so scaled up here, being jostled around. What does it show? It shows that all the particles that are moving it, the air particles, are moving randomly, different speeds. Sometimes it jumps a big distance, sometimes a small distance, left, right, up, down, wherever. So it's all very random in their direction, but also quite random in their speeds. So this random walk, as it's known, and again there's an Excel spreadsheet so you can get the idea, same calculation but just repeated and repeated, you can see you get completely different results where particles randomly walk around, and that's because they're being hit by these random particles. So random walks are kind of a really useful idea. It's how electrons move along wires, etc, etc, etc. So it's happening at all kind of levels. So we're going to do it for gases. The particles are moving within a gas. We know from their movement, Einstein showed that it was just down to kinetic energy and makes the whole lot easier. So the maths we need to do depends on really clear-cut, simple assumptions. So it will only work if these four assumptions are true, which we have since found out that they are. So firstly, as I've just said, but add on, it will only work if you've got a huge number, okay, of particles, of molecules. Okay, if it's only a few, it would be very obvious. If you had a balloon with about 7 molecules in, you'd see the points every time it hit the side of the balloon. So large numbers, we're talking millions and millions and millions. They're all moving, oops, terrible M, moving rapidly, okay, in random directions. With random speeds. Now you can be expected to put these together. You could be expected to name 2 or 3 of these assumptions. That's probably the easiest. Huge numbers of molecules moving randomly. So that means random speed, random direction, or perhaps with random velocity. Sum it up. The second one is that the molecules, they're basically tiny, otherwise it wouldn't work. You need it a bit more scientific. So the way to phrase this, they have negligible volume, okay, so they are tiny compared to, because it's not just they're small, but compared to what? Compared to the volume of the gas, okay, volume of, as it's a gas, let's say the container, oops, excuse me, the container. Okay, so they're tiny compared to the space they're taking up. They are far apart, so that's what that's saying. The next one is absolutely crucial, but it's the hardest to remember, but it's crucial to the derivation. So the time of the collision, or time during collisions, of collisions, saying and writing 2 different things doesn't help. So time of the collisions is, strangely enough, let's use it again, is negligible compared to the time between collisions. Okay, now that can only be true if there is no kind of force of attraction that's measurable between the particles and the wall of the container. So they bounce off really cleanly, there's no loss of energy, those kind of ideas. Okay, and so because of that, and so collisions are, and this is a hint of where the mass comes from, perfectly elastic. Now, that phrase we've seen before, and that's where the mass comes from. It comes from momentum. Okay. The last one is the intermolecular forces only occur during collisions. Okay, so those assumptions are really, really important and basically can start building us up to a model that we can use. So we're going to use this. I would suggest you sketch this in your notes. And apart from the first one that said a huge amount of particles, what we're going to do is we're going to assume the movement of one particle back and forth in its container, and then we're just going to multiply it up to make it random. Okay, so we're going to consider large numbers and moving in different directions with different velocities, etc. So, to make it nice and easy, you may not seem it, but it is to make it easy, we're going to look at the idea of how the particles hitting one wall of the container directly on, so striking it at 90 degrees, striking it and then coming straight off again, without a change in speed, so velocity becomes negative rather than positive, but just bouncing up and down in this box, and as it does so, it presses on the wall. Now, these are moving very, very fast, as we shall find out at the end of the derivation, from the derivation. So it's moving very, very fast, so it's actually hitting that wall hundreds of thousands of times, possibly millions of times a second, obviously depending how big the box is. So we're going to go for a volume of gas that is a nice square cross section, area A, length L, moving at velocity V, and so you can kind of work out, as our derivations we're hinting at, the time between collisions and so on, because velocity and distance. Okay, so that is the main idea. Bring that in, and what we're going to do is go through the maths, but then break it down into a flow chart. Okay, so first things first, make sure you learn those, and then the question may go on to, because that's often the first part, it'll ask for a couple of those, quite commonly. I should point out that on its own, for example, isn't probably enough to get a mark. It might give you benefit of doubt, all the collisions are elastic. However, time and putting a bit more depth in will add a bit more. So probably the easiest, second easiest, the fact that there's only forces when they collide and there's no attraction between them, so there's no potential energy. That might be a third one to remember. That's the most useful for the derivation, but maybe not the easiest to phrase. Okay, but yeah, you could stick that bit with any of them. So what we are going to do is work on this idea here. Okay, so here's our particle. As I say, it's moving with velocity v. It has a certain mass, and that will change depending on what the particle is. So if it is a molecule of gas, which gas? Because they have different relative atomic masses. Okay, now it does link in. I've put some information at the top here, and this will help you visualize it, so have a read. But basically, that length there is what's going to matter for us, and that's our area on the end. Okay, so we're starting with the hard bit. You could think ahead, and this might help. We're going to think about the idea of pressure, because that's both in Boyle's and the pressure law, so it's kind of a fundamental thing. And we know that pressure is force over area, so that is our kind of starting mindset. Not useful at the moment, but that's what we're after. So we want to know the force pushed, exerted on the wall due to the gas. Okay, so what we need to think about is, to get the force, we need to think about momentum. It's got a mass, it's moving, so we have momentum. So if we think of it, and we'll be very specific, if it's moving in that x direction, okay, y direction, z into the page, if we just think about the x direction, it's going to be moving forwards with velocity and then moving backwards with minus velocity, negative direction. So you might want to think of that as your plus, that's your minus, okay, just like we have so far. So what we need for force is force equals change of momentum per second, or more importantly, more correctly, sorry, rate of change of momentum. So that's our background thing. Delta mv equals simply the second momentum minus the first momentum. Okay, really important, because otherwise people go wrong right at the beginning. So that, picking that apart, we've got a minus Vx subtract Vx. So that's actually going to equal minus 2mvx. Okay, so that is the force that changes the momentum. The force exerted on the wall is 2mvx, or due to 2mvx, so plus. It's in the opposite direction. So Newton's third law is just that, whether it's plus or minus. Now, that one most people are fine with, as long as you kind of lay it out clearly. The second one is a bit harder, and what we actually need is not the time of the collision, but the time between collisions. So hit, hit again. So it's that gap in time. So start, 1, 2, 3. Okay, so what we need to do from that is just simply using s equals ut. Okay, so not accelerating, so it's just speed, velocity and time, or sorry, velocity, time and displacement. So t is s over u, there we go. And what we've got for the distance and displacement is there and back. So it's going to be 2L, okay? And we are going to, just to keep the terminology going, it is velocity, but it's velocity in the x direction. Okay, so what we've got going on are two things. We have effectively the impulse. Okay, so we have that that idea of collision with the wall, and if we combine it with time, we'll end up with force. So quite simply, as we said, force is rate of change of momentum. Okay, so we are going to have excuse me, minus 2 mvx divided by t. So in other words, multiply by the upside down version of that, x over 2L, okay, 2's cancel, and we have the x squared. So that force, to just clarify it, force on the particle, okay, is going to be minus mvx squared divided by L. Just be careful you don't forget that. That's quite a common mistake. Okay, so I'm too busy writing and not thinking. That whole thing goes up there. So I'm going to slide my answer in underneath. Apologies there. When you're watching the video, you put yours in the right place. Well, simply enough, we need to just think of it in terms of the pressure being the force over the area. So if we do this, we'll find that force over area. Okay, so that's our idea of shoving it down here, but I will shove it down. Force over area. So what we've got is minus, almost put the 2 in there, mvx squared divided by L times by A. Okay, so there's our area there, length there. Doesn't take a genius to realize that's volume. Okay, so what we've basically got there is that the pressure is linking in with kinetic energy, hint, yeah, it's not half mv squared, but it's mv squared divided by volume. Okay, which simply, for equation 3, this should be 3, means that pressure volume, if we arrange it to make it look more convenient, mvx squared, or v squared in the x direction. Okay, so that is already hinting at our gas laws, yeah, and we've done it just by consideration of a single particle bouncing around. Now, up to that point, that's perfect. That's as far as we can go. We've already got the idea of pressure and volume. We've already got the idea of Boyle's law. Boyle's law's constant is due to the velocity of particles, but that is the one single ideal particle. So what we're going to do is just multiply it up and make it more realistic. So the more realistic bit comes from introducing more particles. So again, from last lesson, capital N is the total number of particles, total number of molecules. Okay, I'll keep skipping back and forth, but think of it as molecules, and I'll explain why in a second. So if they have, and I'll just put in with the same velocity, but I'm going to get you used to using the phrase, so the root mean square velocity, you'll see where that comes from in a second. Okay, then what we've got is simply PV equals, bring that into view, that multiplied up by n, n m v squared in the x direction. Okay, so literally they all have the same effect. So if you've got 12 of them, you're going to have 12 times as many collisions as you do with one. So you're just scaling it up literally as that. Now, if you then think about the particle itself, well, particles really are going in any direction, so a diagonal direction. So what we've got is they are thinking about it in a three-dimensional form. So we can find the actual velocity, okay, which we're going to call c. It is not the speed of light. C is traditional though. Sometimes you might see c with a bar on the top, but it doesn't matter too much. Okay, for ours we'd say without. So for this, the actual velocity is going to equal the velocity squared, c squared, so the mean of the square, we'll come back to that in a second, is going to be the x direction plus the y direction plus the z direction, all squared. Okay, that's a z at the bottom, not a 2. So x, y and z direction, which means that if I want to get this kind of crux idea together, if I want to think about the velocity to put into my equation there, then what we've got is effectively we can say that's approximately 3 general velocities squared. Okay, so if we wanted to get the root mean square value, what I actually need to do is rearrange that. So I can get v squared equals a third of c squared. Okay, so I'm actually finding the average by this, finding the average in terms of v, so I can put into my equation. So that is a more general phrase because I did it in the x direction, but that could be the y direction or the z direction, so I'm just going to call it the generic v, and that v to subscript into there goes in straight, nicely straightforwardly. The important bit, okay, is that this itself is obviously squared. Okay, if we wanted to talk about the actual velocity of a typical particle, okay, so the ideal of all of these, this mixed together, then what we actually do is this RMS value here, okay, with a little subscript there, sometimes C, they kind of are a bit loose and free with this, is you need to find the square root of C squared divided by 3 because there's 3 dimensions. So this is the root of the mean of the squares, and this is where RMS comes from. Okay, this is actually a geometric mean. Okay, so it gives you a slightly different way of doing it, or near enough geometric mean. So it actually gives you far better value for velocity, typical velocity. Okay, I won't say average, but typical velocity for any particle moving at any speed in any direction. Okay, so I'm just going to put that into brackets, and this is the idea of note why the phrase RMS speed comes in. Okay, and we'll use it when we look at AC theory as well with electricity. You'll see it's a very similar idea, so it's literally describing how to do it. You find the root of the mean of the squared. So, okay, let's go into the, I should say that's an extra, so you don't need it for the proof. So if we put that into here, okay, so if we take that equation, we substitute it into there, then what we end up with PV equals a third NM, and I'm going to put it as the C squared, and just to make it kind of traditional again, that's that hint that it's not just C squared, it's the root of the C, so it's this kind of typical value. Okay, so just put in as typical particle. Okay, and that is the equation for, excuse me, I've missed a very important bit, negative. Okay, so that is the equation for Boyle's law, the full equation, in terms of particles, the mass of each particle and how fast they're going. Okay, so if we know the velocity of particles, or if we know these, we can tell how fast particles are moving. And actually this is very, very accurate as long as you stick with these assumptions, particularly this bottom one. So these need to be fast moving, they need to be a dry gas, there's no stickiness, they don't stick to the side or each other, because then you're talking about intermolecular forces. So it won't work for vapors, but it will work really well at predicting movement in normal everyday gases. So as I mentioned before, I'll just put in here, because it's a nice slot, it's negative as this is pressure by the wall. Okay, if we cast our mind back onto the particles. Now, normally we measure what the particles do to the wall, so we will just put in therefore pressure on the wall is the version that you'll see in the data book, which is exactly the same but without the minus. So a third, a third NM C squared bar. Okay, so this is where I was going to leave it nice and clear, but I've given you a space up there. That's where that goes in there. So that is that typical. Okay, don't say average. So put that not average. That will get you lose you a mark in the exam. We need to talk about the root mean square velocities. Okay, bit of a mouthful. There is a trick. You cannot mention velocity at all and talk about its energy. More of that later on in this section. So can we bring it together? Well, yeah, if we think about what that equation represents, that's the number of particles, that's the mass of each particle, so put them together, that's going to give you the mass of the gas. So PV is a third mass of the gas, using the same symbol that we've done before, C squared bar. Okay, so if you literally can measure the mass of your gas, you know the pressure and volume that's measurable, you can get that. Okay, so we can do that back and forwards. Or, again, taking us back to that simple idea right at the beginning, and again this links in quite often with questions, they'll talk about the density. Well, density is mass over volume, so we can simplify that even more. We hinted at it before and said it shows it's proportional, but we can actually say it's now, again just be careful, that's rho, that's P, it shows they're actually linked. Okay, so pressure is directly proportional to density and the movement of the particles. Okay, the movement of all of the particles, the typical particles.